Good evening, everyone. My name is Uday Bhaskar. We still are 2 minutes away from 18:30, 6:30 p.m. So I just thought, first of all, I'd greet all of you, welcome you, and request you to put your phones on silent. And the additional request, based on recent experience, if you have any alarms on your clock, either for medicines or to make calls or find out about what's happening at home or elsewhere, you just might want to turn your alarms off. Because I learned, to my dismay, that you can keep a phone in silent, but the alarm will still go off. So that is just one input due to this evening's talk at the IIC. And thank you for taking this suggestion about putting your phones on silent and so on. Sometimes I've been accused of overdoing this question of trying to start on time and making phones on silent, but thank you for bearing with me. Before I begin, let me also acknowledge the presence and welcome, amongst others, the President of the IIC, Master Shyam Saran, the Director, Mr. Srivastav, and you can see that I've been shanghaied, that I'm sitting over here, but it is part of IIC's, shall we say, ethos. But at the outset, let me sort of say that chairing a session with Commodore / Professor Paulraj as the lead speaker is rather, shall we say, presumptuous. So I'd like to introduce myself as someone who is the Sherpa, coordinating this event with two very illustrious panelists, one Professor Paulraj and the other is Ms. Aruna Sundararajan, who will be the lead discussant and the moderator. So that's the frame of reference. Very briefly, the subject for our discussion today, I'm very glad to see the turnout. And those of you who are sitting at the back, if you want to move up, please do so. There are enough chairs. Is the semiconductors and their relevance as far as the current times are concerned. Those of you who are domain experts and know all about semiconductors will need little introduction, but variously described as the lifeblood of the digital economy, the spinal cord of the 21st century, and various other, I would say, ways of focusing or highlighting on both the criticality and the relevance of the semiconductor. And it has multiple implications, not only in its technological context, but also at the level of what you might call as the strategic orientation, not only of the major powers, but in many ways, I would say the current decade, if that's a reasonable time to locate the kind of technological advances and innovations that are taking place, and the kind of paths that are forged. Path dependency is a very interesting kind of concept. And the semiconductor offers, as I said, many such relevances. And to walk us through this particular subject, I have great pleasure personally in introducing and welcoming in our midst Professor Arogyaswami Paulraj. Some of you know him personally, those who do not. He's a very modest man, and for me it's a particularly, I would say, special privilege. I can't but share this tribal impulse, which is that he is a fellow sailor, retired from the Indian Navy many years, senior to me, of course. Apart from that, he's also, like me, an electrical officer. And the tribal part underlined is that in the NDA, we associate ourselves with squadrons, apart from seniority, which course, which batch, all of that. But we go by our squadron affiliation, and we are both from Foxtrot. So anybody here who is either from Foxtrot, there you are, some hands, or who will later on, I just want to place that there. But he was in the Indian Navy, and if you look at that slide there, amongst many accomplishments, where Commodore then Paulraj stood out was this APSO sonar. He was the brains, the lead person, the father of this project. And this was India's first indigenously designed and built sonar, which is for anti-submarine detection. In its time, it was a remarkable breakthrough. But for a variety of reasons, I think the system was unable to acknowledge, recognize, support what Commodore Paulraj had done at that time. And a few years later, he moved on to Stanford, who in many ways I would say he blossomed in Stanford in a remarkable way. From 83 Apso-Sona to where we are now is 40 years, 2023. And there, as I said, his track record is absolutely outstanding. He is the father of MIMO. Those of you who know about MIMO, globally acknowledged. His CV is extraordinary. He deliberately called me aside and said, Uday, you'll be in trouble if you make my introduction more than 3 minutes. So I'm walking into trouble by telling you that if you look at his accomplishments, he is one of the few people in the world, apart from his Padma Bhushan, which the government of India had awarded him for his outstanding work. He is a recipient of 4 major prizes, telecom, engineering globally. He's got the Marconi Prize, which again, some of you would know is the equivalent of the Nobel when it comes to telecom. He was also awarded the Faraday, the A.G. Bell Hall of Fame. I think I'll stop here. Bain in Silicon Valley started 2 startups which took off. But what he will do today is to help us understand the complexity of the semiconductor industry and what are the challenges ahead, both globally and otherwise. And to help us understand the subject a little more from an Indian perspective, I have great pleasure again in introducing and welcoming Ms. Aruna Sundararajan, senior member of the IAS. She retired as the Secretary, Telecom Steel, has also been in many ways the person who led the 5G effort as far as India is concerned. Currently, she is chairperson of BIF, ma'am, would that be right? And as I said, her own track record and her contribution, I think, in this sector has also been acknowledged. So we have requested her to be the equivalent of the lead discussant and the moderator for our session, to perhaps talk to Commodore Paulraj about his own remarks and maybe tease out the relevances for India, if you think that's possible. Now, in keeping with the IDSA's, the India International Center's, kind of timelines, we will close at 2000 sharp. Because of that, Commodore Paulraj will speak for about half an hour. Ma'am, 15-20 minutes, and then we'll go into QA. You can take it forward. So on that note, Paul sir, may I request you and hand over the floor to you.
Mr. Shyam Saran, Life Trustee and President of India International Center, such a great institution in Delhi. Mr. C. Vastava, Commodore Bhaskar, Uday, Bhaskar, our chairman for the session today, and Secretary Sundararajan, our moderator. I wish to recognize also some other key department leads. I can see Secretary DST here, Abhay Karandika, there. And I don't know, Secretary Mittal's around. I think he was supposed to come. And Secretary Krishnan, I think, may show up a little later. So, very distinguished guests, ladies and gentlemen. So, many thanks to Bhaskar and Secretary Sundararajan to help out. Bhaskar, as many of you know, is a very prolific commentator on geopolitics. And Secretary Sundararajan is one of India's most distinguished civil servants. I had the privilege of working with her from 2017 and 2018. So it's indeed a privilege to be here today and to share with you my understanding of the global semiconductor industry. I know the traffic, I face a lot of traffic. Some of you must have had a tough time coming here. Thank you for joining us. So our efforts in semiconductors started about 40 years ago in India, but various reasons we've not been able to break through. So now there's a new effort. And so I won't be touching, I'm a little bit involved with it peripherally. I won't be touching what's going on in India, but just talk about the global industry. And a little bit about, some ideas about what the path will be for our country. So as Bhaskar mentioned, I was for many years in the Navy. Most of it I did building sonars, but I started 3 labs, one for the lab for AI and robotics for the DRDO, very briefly. And that got me diverted into the LCA program and other things, but also helped start CDAC briefly, and also worked with Bell to start their central research labs. But I was always interested in mathematics, and I was fairly well known in the United States for my math work. So I always had an opening at Stanford to join the faculty. I went there in 91. And by some particular chance, very quickly, and I think it's something to do with my background in sonars here, the idea of MIMO came. It came through some experimental work I was doing for DARPA. And initially, it was actually roundly rejected. Stanford thought this was a great idea and a good patent to license. All the world's companies came there and they walked away saying it'll never work. But ultimately it took off, and I was just one number there. Now, mine was the first patent. Now there are 577,000 patents worldwide. This includes both live and maybe expired patents, but maybe live maybe of 300,000 patents. It is the most litigated technology in the world. There are hundreds of billions of dollars of IP fights going on around MIMO. So there are about 20 billion devices in the world today in use, from phones to laptops to pads. And so it's certainly also, it's now entering cars and machinery. So it's a very big ecosystem. Both the Wi-Fi Alliance and the Cellular Alliance, Mobile Alliance, claim that the economic impact of both mobile and Wi-Fi technologies is 7.6 trillion today. So it's a very large impact. So I've been very fortunate to be part of this industry. As Bhaskar mentioned, I did two startups. Then I was heavily involved with US government policy through the national academies, quite involved with China. I was involved with their academies, and also sat on one company board and also an advisor to some of their VC funds. And in the United States, I've been sitting on boards of smaller wireless companies, mostly in wireless. I'm often using MIMO, but also with venture capital. I'm still active with venture capital in the United States. And also a little bit in Israel, when they were starting their industry about 25 years ago, I was a little bit involved on their fabless. They've done very well in fabless. They don't care very much whether the company remains in Israel or gets acquired. So far, they have $37 billion acquisitions out of Israel. So brought a lot of wealth to Israel. So broadly about the industry, I'll talk more about it. It's a very, very important industry. Critical, I think, going forward, but also extremely difficult to enter. So the evolution, started in 1947 with the three people there. One is Shockley, who was sitting, and then there's Bardeen. The third person I don't know, but they were the co-inventors of the transistor, 47. For some reason, Shockley then joined the Department of Defense and began to design sonars like me. But around 1965, he landed up in the Bay Area with Santa Clara. I think his parents lived there, and started his first company, the Shockley Labs. And he recruited some incredibly good people, Gordon Moore, Bob Noyce, and many others. And but I think he was a terrible manager, so that group left and picked up some money from Fairchild, and they formed the Fairchild Semiconductors. And some of their products I actually have used in India. But by I think a little bit towards late 1960s, 1969, they again broke away and formed Intel. So Intel was a blockbuster company, and then I think really took off from there. And Intel was the first company to sort of invent venture capital. So when Intel was formed, they got money from Arthur Rock and a couple of people I know who are still alive who gave them money, and Intel had a huge IPO, and those people made a lot of money. And therefore, the whole idea of venture capital was born around the Intel's exit. And of course, now it's much larger. And so today in 2023, I have been helped by many, many people, and I'll just mention and recognize a few of them. On the bottom left is Jim Gibbons, who's 92 years old, but a very, very, very honored dean at Stanford, and the person who recruited me at Stanford. So when Shockley was setting up his labs, Jim set up the R&D at Stanford, the research at Stanford. So they were actually partners. And Jim stayed on in Stanford. Later on, of course, he was on board of many companies. The other person next is Federico Fagin. Federico Fagin and Ted and name will come back to me. They were the co-inventors of the first microprocessor, the 4004 chip, which some of you may have used, which I've used also. So TEDHOF. So TEDHOF and Federico Fagin are the, and I've been working with Federico for a long time through many committees. The third one, of course, is now the CEO of Intel, Pat Gelsinger. I got to know him because Intel bought my first company in 2003, and he was the CTO then. Remarkable person who left Intel, has come back, and he knows India very well. We have come to India together many times, and I think always a friend of India. And the next one is Andy Viterbi, the founder of Qualcomm, the co-founder. So me and Qualcomm always had a love-hate relationship to one point, because Qualcomm was pushing CDMA and I was pushing this new idea called MIMOOFDMA. And finally, we had to displace their technology. So there's always this tussle between Andy and Qualcomm and my own companies. But he's a revered figure. And the last one is Henry Samueli, who is the chairman of Broadcom. They bought my second company. I'm still very close to him, and we just met for dinner a couple of weeks ago in Washington, D.C. I know many more people, so it has been a beautiful ride at Stanford and the Silicon Valley with all these amazing people. So just a word about semiconductor technology. I want to read it out. So semiconductors are a uniquely important enabling technology, fundamental to today's and increasingly tomorrow's economic and national security infrastructure. AI and computational techniques powered by semiconductors have also begun to exponentially accelerate advances in science and engineering. This is the new aspect of semiconductors. The gap between those who control semiconductors and those who do not is rapidly widening. So it's important to keep in mind. So let me now talk a little bit about the enabling part of semiconductors. So, I mean, because it's everywhere, but certainly in information technology, in cell phones and internet, that is the top left circle, it's done very well. So all of us, it's transformed India. We have the digital transformation in India is driven by this revolution. So it's been a huge boon to the world, and I was mentioning the economic impact of 7.6 trillion in a 110 trillion world economy. Then, of course, it's entered medicine, robots. I'm going to have a surgery for my knee on January 10th, and that's going to be done by a robot. And it's all semiconductors inside that. AR, VR, we know about. And then the bottom is AI, the other circle, and that is the new kid on the block. And that is becoming enormously powerful. And I think its impact on the world will be more than wireless and internet. It's going to be more fundamental, and there's lots of controversy around it. I'll talk about it. It's also entering cars. They say in a few years, 20% of cars' costs will be in semiconductors. Autonomous driving, so many things. Because all of these feed to national security. Nothing concentrates the mind of any country than national security. And national security is heavily dependent on semiconductors. Another part of is also an accelerator. So it turns out that AI, in the recent versions of AI, and very high-speed computational methods are begun to revolutionize science and engineering. Whether it's chip design, or there's a protein folding, or modeling neural network growth in the brain, or that's simulation of electric motor, or hundreds of applications, we're now finding that the combination of AI and very high-speed computations are beginning to accelerate all these things. Some of the chips are extremely complex. They have something like 80 billion gates and multiple metal layers and trillions of connections. Optimizing the physical layer is very complex. And in order to take 1 year, people say they can now do it in a few days. So it's accelerating a lot of advances now. And therefore, it's going to increase the gap of people who have the technology versus who do not. So a little bit about the industry. The first segment, and the largest segment of the industry is about $300 billion revenue, is the fabless segment. And these are my own two companies were in the fabless. I've always been involved in, currently also, only in the fabless segment, mostly in the US, a little bit in China. And this is it's a chip design. Again, is dominated by big companies like Qualcomm, NVIDIA, Broadcom, MediaTek, AMD. HiSilicon is a Chinese company. And almost all of them, and many more, have operations in India. But these are just engineering outputs offshore. But the entire control of intellectual property and all the value addition and the revenue is all incurred by the headquartered in the country headquartered. So Qualcomm, NVIDIA, all American companies. So the United States commands probably about $250 billion of revenue because of the dominance of these companies. And so I know most of them fairly well, and incredible collection of talent. Many of, I would say something like on the average, something like 25% of the engineering work, not the marketing and the business, which is also very important. Engineering work gets done in India. In fact, Qualcomm's R&D chief now is my student, Dhananjay Gore, one of my doctoral students from Stanford, who now heads Qualcomm R&D. But also remember, these are completely islands in India. They have nothing to do with India. And they're completely controlled by their home country. So in fact, they're here, we get some payroll. So I think the payroll out of these companies who operate in India is probably about $20 billion. That's a lot. But we don't get any other strategic or any other value out of them. The second part, of course, is the part which is also much in the news, is the manufacturing in the front-end fab. The front-end fab is where the diffusion takes place, and that's the high-tech fab. And I would say both fab and fabless, every idea was invented in the United States, but US now has begun to fall behind, largely because our companies like Intel and Micron are Wall Street controlled companies, and we're not being able to invest in R&D because any R&D investment is less profits and poor stock price. So we've been in trouble. So we now have a CHIPS Act of $53 billion to try and boost this area. But the dominant company in the world today, it all came from US. Morris Chang, a Stanford PhD, worked at Intel and took back some people. And I know Morris. I used to go and beg him for better pricing on my chips because he would give me, I was low volume, I would get very bad pricing from him. But he's a revered, almost a demigod in semiconductors, lives in Taiwan. So TSMC is the dominant company in logic. They now have 3 nanometers technology. US is not anywhere near. Intel is also high revenue. Again, lots of technologies, but because we neglected some investments, we have fallen behind TSMC. The next two are from South Korea, SK Hynix and Samsung. They dominate the memories. TSMC dominates logic, they dominate memories. Global Foundries, another American company, but it's got presence all over the world. And UMC is another Taiwanese company. SMIC is a Chinese company, and there's also Yangtze, also Chinese. And I would say, in general, this is getting more and more consolidated. There were much more fabs, but many of them have been pushed out of the market. The bigger guys get bigger, and the smaller guys die. The third part is the low-tech part of semiconductors, called the back end, where once the fab wafers come out, we test the wafers. A lot of it is automated. Then we do packaging, and sometimes we may do multi-layer packaging, and getting more and more complicated. But it is generally the deep end, the front end companies don't touch it. They normally they give it to outsourced companies, OSAT. It's about $30 billion. I should mention, fab is about revenue per year is $280 billion, and about $30 billion is with OSAT. AC, I think, is a Taiwanese company, dominant. Amkor is American, and JSAT, PTL, and the rest of it is all Chinese. They tend to dominate this. We are, ISM has announced a deal with Micron, where they're going to do some of this assembly and test in Gujarat. So we have funded it heavily with about more than $2 billion. and we'll have to see how that goes, but it's a very good start for India. But it will be probably mostly assembly line labor that we will have. The supporting segments are the design, EDA. These are massive companies, Cadence and Synopsys. Emprion is a Chinese company, but they're still nowhere near these two giants. Again, these companies have a lot of offshore R&D here, but they're all over the world, and they control this market. I generally know Cadence for a long time. Liputan, the chairman, was on my company board, so I know him well. Manufacturing equipment, the big battle is on lithography. Lithography is what where you imprint these patterns on chips. This has become very high tech, and the dominant company here is ASML. It's a Dutch company, and that the picture below is of an ASML. I'm not sure whether it is the deep UV, extreme UV or deep UV fab. Extreme UV, that box is right side of a trailer is $150 million, and so they are the key to 5 nanometers and 3 nanometers. China has been Americans have been able to stop them from selling to China, but they lost a lot of their market to China. So there's lots of politics going on there. Right now, China doesn't have that doesn't have this instrumentation from them. They do have deep UV, which is the earlier generation. Then CVD, chemical ion deposition. There are lots of companies there. I'll mention ASML is lithography, Applied Materials, American company. So we have lots of control of CVD and ion implementation. Tokyo Electronics and Japanese companies are a very strong company. AMEC and SME are Chinese companies, and not quite at this level, but they're trying to catch up. And there are a lot of supplies, silicon ingots and gases. I should say the supply chain in a fab is something like as much as 1,000 companies. So and they're spread all over the world. A lot of it is in China, but certainly United States, Europe, Japan. Japan has got a lot of the supply chain of fabs. And of course, there are ingots and gases and so on and so forth. So the market size, total market size is 600 billion, but just the fab size revenue is about 300 billion. I mentioned that earlier, a little bit, maybe a little less. So only the fab. So South Korea, because they dominate memory, and you have lots of memory in your phones and your laptops, about 28% of, I think it's about 290 billion is theirs. Taiwan with logic is about 22%, and Japan is about 16%. They were this number came out of congressional records. Sometimes they get doctored by because we always want to tell the congressmen to give us more money, so we always push the Americans down and expand others. So I'm not sure about Japan being 16, maybe less. Then China is 12%. That's probably a little high, maybe 10 to 11%. Then US can put 11%, maybe a little more than that. Europe, which is a big player, crunched down to 3%, and everybody else in the world is 7%. So essentially, it's going to become a Taiwanese, US, China, and South Korean industry. Everybody else is going to get crushed. So technology, lithography, deep UV took us to about 12 nanometers, and that's what Chinese have, but they've been also trying something called argon fluoride technology. I'm not sure where they are. Extreme UV is the gateway to 3 and 5 nanometers, which are now both in production, and that is only from one company in the world, ASML, and they depend a lot on Zeiss, the optical company. So there's lots of optics, and in fact, I would say ASML has DNA going back 100 years in it. That's why they could do it, because there's tremendous amount of optics. You're telling me. Optics. It is, so they dominate. In terms of node size, that's the size of the feature size. 20 is kind of routine, and almost all countries have it. 7, China just broke through to it. I'll mention that later. 5 is in production, good yield. 3 nanometers is low yield, but going into production. I'm involved with a couple of companies which are actually doing that. In terms of gate design, the planar was invented by Bob Noyce, who, by the way, is also a winner of the Faraday Medal. But FinFET, about 6-7 years ago, and Gate-All-Around FET, these are the structures which make this very low node size possible. And gate density, we're already sitting at 160 million gates per square millimeter. So it was incredible achievements. So everything in this is going exponential now, and sometimes say double exponential. So some of the technologies in terms of gigaflops per watt, I mean, 25 years ago, a gigaflop was considered a supercomputer, and you needed hundreds of kilowatts to make it happen. Now you can do 36, 40 gigaflops in 1 watt in a chip. And this is the large language models, which power ChatGPT and things like that. That model size is also growing rapidly. Now it's about 1 trillion model size. It's incredible. And it's going to go much more. And that is the reason of the semiconductor. It turns out, if you want to make this very pervasive AI technologies, you need to build a lot of machines, because most people want to do it themselves. They don't want to share it. It's so secretive in terms of models. These are so power hungry that if you try and do what we do today in computing, we'll have to double the entire global output of power. In fact, Elon Musk keeps saying the problem of AI is not computers, it is copper, because even if you can set up nuclear power plants, you need copper to run the power lines to these things. So therefore, the key is semiconductors to make AI happen, and because semiconductor advances can drive down the power, and that will make AI more feasible, I mean, the large language models. So that's why semiconductors and AI are heavily linked. Gates per chip, I mean, now we're probably at 100 billion gates per chip. In terms of AI apps is where a lot of the attention is today. Autonomous systems, in cars, it's still not working very well, despite hundreds of billions that are invested. They're still not quite there. We have a little bit of trials going on in San Francisco. They get into trouble. So we're still probably 3 or 4 years or 5 years away from really robust autonomous. But a lot of that is for defense. That's where all the money is going. Generative AI, which ChatGPT kind of stuff. So this is going to, this has been quite revolutionary. It started off with, writing essays and toys. But now today, it designs pretty good code. It writes code. It builds chips. It designs chips. It seems to be able to design new molecules in pharmacology. It's doing so many things, which is surprising in some sense. I don't understand it enough. I know the older AI, neural networks, somewhat well. There's new stuff. New stuff is exactly the old AI, but only with concepts like transformers and attention. It's not that different. And I keep joking that MIMO, where I work, the underlying mathematics is extremely abstract. In fact, I don't understand any of the papers anymore. But AI, the ideas are very simple, and the math is just matrix multiplied. But they're so large, you need a lot of computing power. And then computational, anything you touch today is going to getting accelerated by AI. And what will take a year, you can do in a few months or a few days. So this is going to push the countries that can control this, accelerate much further behind those who not. And so the reason why the United States is so worried about semiconductors is all this acceleration of technology. So their leadership is going to grow. They can control it and not let others have it. So the industry snapshot, R&D, about 600 billion revenue. R&D is about 200. I think it's more than that. But R&D at every point in the supply chain. That's a lot. 200 billion is now 10 times what we spend in all R&D in our country. The capital investments about 2 trillion, 1 trillion by China, another trillion by US, Taiwan, and South Korea. And already you can see about 250 billion is already called for, but it will be about a trillion at least over the next 10 years. The 5 nanometer fab is around 20 billion today. No country is self-sufficient. I mean, it's impossible. Whether it's in fabless design or fab design or in fab, many countries are involved, and no country can be self-reliant. It's a matter of any country is only about, even the United States, to join the club and participate in the club. US has 12%. I mean, India could aim for in 10, 15 years, 2 to 3%. That would be a lot. But no way we can be self-reliant. Increasingly consolidated. So at one time there were hundreds of companies. Now there are only a few companies on the fab side and the fabless side. because the more bigger they become, the more money they can spend on R&D, the faster they go, so everybody else gets left behind. I was telling somebody, at one time, US had 100 aircraft companies. There's only one left really in US soil, that's Boeing. Consolidation takes place. So whether it's in revenue or in talent is probably the most important thing, or in R&D, getting highly consolidated. So people are being left behind. All the value realizations in IP, there's no value for labor. It's only for IP. So only in IP you can enter this thing, or ticket to entry. Otherwise, it's very difficult. It's also ultra competitive. Only the toughest survive. There's a book by Andy Grove, former CEO of Intel. You might have heard the name. It was only the paranoid survive. And my own companies, I keep saying, quite often when I walk in the morning, I was always at Stanford, so my job was protected. You walk in the morning, you're not sure you'll survive the end of the day because you're running out of money. And every now and then, US has this problem, like we had this internet burst in 2001. We had the Lehman Brothers 2008 debacle. They're right in the center of my companies, and always very difficult. And your valuation goes from 1 billion to 100 million to 10 million overnight. Just keeps going around. It's a tough journey. Only the paranoid survive. So now a little bit about US versus China. China has about 20 major fabs. SPIC has a lot of it, Yangtze and others, and 20 other fabs. Chinese put a lot of money in the provisional government to start fabs and wasted a lot of it. And so I think some of them are just living dead, but they have to have mainline fabs. TSMC has fabs in China as well as Samsung. It's good to understand how they brought them in. It's amazing what all they did to bring those fabs in from Taiwan and from South Korea. There are about 10 major fabless companies, HiSilicon I mentioned, but also Alibaba and others. They are some of the chips are getting competitive with US, but I think I would still say behind. There are lots of other fabless companies. They seem to have now 7-nanometer logic. Their latest chip phone, Mate 60, has a chip with 7-nanometer. We know that. The question is, how do they do it? Their deep UV technology could do it, but it'll be bad, so we're still trying to figure that out. That came from SMIC. They have 12-nanometer memory from Yangtze. They're one node behind the South Koreans who are at 7 nanometers. They are probably investing $10 billion in fabless per year, 10 billion. And how they did it was, I was involved a little bit in their Tsinghua Unigroup fund long ago. And as some of you may know, the CEO has been locked up for some reason. But what they did was they told all these big companies, Tencent and Alibaba, and that don't put money into fluff companies like delivery apps and all that. We only want quantum computing and semiconductors, this very high-end, deep technologies. So they are putting money into those things, kind of mandated by the government. I'm not sure exactly how it's done. 10 billion fabless. About 100 billion fabless per year on the fab side. And this Mate 60 was a surprise that they could build this in 7 nanometers. Their AI chip is pretty competitive with Apple, but the 5G chip, 5G is full of math. Somehow that chip, they do a very good job of infrastructure, the Chinese. But getting chips on phone is very difficult because of the low power. You can't have much power. So apparently they're still way behind Qualcomm, maybe 2 or 3 years. On the US side, we lead fabless very heavily. I think nobody touches it at this point. Fabs are competitive with China, so it is of course of great concern. We only invest 1 billion fabless a year because we were about 10 billion when I was raising money. Lots of money was available. Now we find that we cannot make money in fabless because we can only make money. We can never go to a market on our own because everything is consolidated into single chip in these phones. You have to sell the chip to Broadcom or to Qualcomm, and they're not going to buy your IP and put it in. They basically buy you off. And then because of competition, there's not much return on money. So fabless funding is shrinking in the United States. It's a big concern. US government is trying to look at it. In fabs, we've got 100 billion investments happening. US government has got CHIPS Act, $53 billion. So I think that's going to get revived. So, of course, the US is very worried about China because the semiconductor AI nexus is of huge value. So they want to block China, and many of you know what's happening. somehow you should read the October 7th, there was a document, I think a 200-page document. They list every Chinese company, what they can be given, what they cannot be given. We can't block China fully because we take these phones, a lot of Chinese components. So they understand this. They have hundreds of people in Department of Commerce, Department of Justice, and CIA looking at all these things. And so they're pretty savvy of what's going on in China. So it comes lots of entry barriers. But the key to success is innovation IP. You can't get in with any other. That's the only ticket you can go in. And so important for this is experienced talent. It's very difficult in a country like ours, which has no base really, to bootstrap on our own. So I think we should do what the Chinese did, what the Taiwanese did, what Korean did. Go and grab people out of Americans. Right now, of course, Chinese are gathering people out of Taiwan, because Taiwan has got an ecosystem, and the Koreans are doing the same thing, and they're all gathering from each other. And so people is everything. You don't have the people, you're not going to make anything happen. We have the raw talent in our country, but bootstrapping is almost impossible. We got to bring people back. That's what they did. Investments, you know the numbers, is very high, and but nevertheless, I'm sure we can find it. We're going to be a large economy. And it's also foundational research. I mean, the United States has these top universities. I should mention Stanford, of course, and I should mention MIMO came out of Stanford. But top university Stanford, and Chinese have very good universities too. So these are a lot of engine of innovation comes from these companies or universities. So it's also very important. IPR. So IPR, you build anything, once you get to about 50 million revenue, you'll be targeted for IPR, because just MIMO itself has got 577,000 patents. You do anything in semiconductor, you're going to face 100,000 patents. How do you get onto them? So we need, since Chinese have spent a lot of people to figure out all these things. And when they figured it out, they discovered that, I won't mention the name of an American company, was actually double dipping on their IP revenue, and they took them to court and won a $1 billion lawsuit. Then Taiwan and South Korea learned the same trick, and they also took the same company to court and got $1 billion out of them. We can get a few billion if we get our act together there. Competition from incumbents. That's, anything you do, you're going to face the Nokias and the NVIDIAs, and I'm taking fabless. Or if you do anything in fab, you're going to face, if you do high node, will generally be Chinese companies, because they're going to dominate the lower end. Below 20 nanometers and better, lower technologies, they're going to dominate, so we're going to face them. A lot of competition. M&A is another problem. That is, you build any company up to some level, usually the MNCs will buy them off because they like the team. So we are only real in our country if we have Indian headquartered companies. So any company grows and they get bought off. So far we had about 7 companies in India. I know all of them. But all of them, when they get to some level, not even revenue, they get bought by the Intels and all that. So question is, how do you prevent that or do you reduce that? It needs a lot of sophisticated thinking. We should go to China. They know how to do it. WTO. That's another requirement. I think generally everybody's forgotten about WTO, but technically you can't do protection except for government purchases. So I think at this point, I think Americans have walked away from it, and the Chinese are probably not also. And the geopolitics. But entry barriers are huge, and I cannot underline it more. Okay, so I won't talk about India, but I want to say this one thing. We absolutely need to enter this industry. We are a large country with enormous talent and potential, so we can and must do it. But to succeed, we need to thoroughly understand the many and the formidable entry barriers, and then shape a path to success. Our path will not be Chinese or it will not be Taiwanese. It will be different, but it has to be modulated by how the industry functions today and all the barriers that are there. So that I'll stop and say thank you.
Thank you, Paul sir. And I'm sorry for using AI to put a 7 p.m. alarm on your phone. You know, one of our young naval officers gave me that tip, so I had your number, so I apologize for that. But more seriously, I just want to thank you for a very lucid presentation on a complex subject. And I'm sure that there would be many takeaways for people seated around this table, many of whom are part of the movers and shakers of the current Indian effort. But I'll get back to that later towards the end of our session. But may I now invite Ms. Aruna Sundararajan. Ma'am, the floor is all yours.
At the outset, thanks to the chair, and thank you, Professor Paulraj, for that comprehensive and informative address on a topic that's not only at the center of debate and discussion globally and nationally almost every day because of the stakes that are involved. Certainly, global technology supremacy and dominance is something that is at stake. But I think in this case, the stakes actually go beyond. As Professor Paulraj had indicated in his slides, it's really about securing one's economic future. It's about securing national defense. And really, if we look at our day-to-day lives, it's also about, trust and personal privacy. So a large number of aspects are, become critically involved in this. This subject also has huge salience for India. We know that over the course of the last year, the policymakers and the political leadership has been putting its heft behind evolving a semiconductor industry in India. There have been a number of statements about the creating an enabling environment, resourcing this industry adequately. And, for my own part, I can definitely say that from 2017, when I was initially involved with the IT ministry, and we were trying to get the semiconductor fab industry going, till now, I definitely think there's been a lot of change. It's definitely become much more ambitious, much more aspirational, but also we're beginning to see real commitment in terms of Government of India endeavoring to create the necessary infrastructure and the resources. The key objective of this session today, as Professor Paulraj had indicated, was really to raise awareness about what is the global state of play, where is India at, and what would be a pragmatic roadmap for India. He, of course, in his disarmingly modest way said, and in a very low-key manner said, there are huge entry barriers. And even if we achieved, accomplished 2% share of the market, that would be huge. But that's not to detract from the criticality of those statements, because clearly the takeaways for me were, if one were to ask, is this doable? Yes, but we have to be realistic. If the US at 12% share of the market is finding it difficult to grow that market, and Europe is at 4% and struggling to increase that, then I think we have to be pragmatic about what India can achieve. I'll certainly come back to that, and I'm sure there are very informed discussants here who will want to perhaps take this up at greater length. But I'll definitely like to say that Professor Paulraj, apart from all the accomplishments that were laid out initially by the chair, I think he has been a person who has stayed actively engaged with the technology leadership and the geostrategic leadership in India. And that is why I think when he says this, I think it's all the more important that we here, whether it's policymakers, decision makers, influencers, need to take this with the requisite gravitas. He has, of course, laid out the evolving global landscape. Although he said, I will not speak much about India, I'm sure in some sense the debate will come back to India. He, I think, deconstructed the constituent elements of the industry, the building blocks, who are the key players. And of course, all of us would have noted that there's no Indian name over there. He spoke about the magnitude of resources, 100 billion a year. We've just heard the US, after the CHIPS Act, commit about 52 billion. We've heard separately the US Science Foundation commit another 45 billion, but we've heard that the private sector is actually talking about something like committing an additional 200 billion to make this happen in the US. And although Europe, after its CHIPS Act, has not really put out what would be the budgetary implications of that, we do know that member countries are beginning to look at this more seriously. And I was just reading that the leading private sector companies, whether it's Intel, Micron, various others, have already committed to setting up additional facilities in Italy, in Germany, in Spain, in Poland. So clearly, there's a lot of action happening, and therefore, we need to keep this in mind as we chart our own path. Professor Paulraj also laid out what are some of the key challenges and barriers, because this is not a trivial challenge. It's a challenge at multiple levels, ranging from infrastructure to talent to resources to technological leadership, to having the supporting ecosystem, etc. So I think a lot of work will have to be done by the policymakers and the leadership here in India to see how we can at least make the initial entry and try to garner a realistic share of the market. So, is it aspirational? What India has been talking about? Hugely so. Is it doable? Yes. But is it a low-hanging fruit? Not in the least. Is it easy? No. And in fact, Professor Paulraj had specifically said only the toughest survive, and this is not for the faint-hearted. So, while there have been recent political commitments made at the highest level, do we have the requisite stomach for actually going the full length is something that we really have to introspect about. He also said something which is definitely of concern, which is that while this whole debate had gotten accelerated because of the geopolitical challenges and the fissures between US, China, we know that the advent of AI has really, it's become like a race against time. What little luxury of time we had is no longer there, because clearly the gap is going to widen. And so we will need to move much faster. What was interesting to note was that he he alluded, I think, at several points in his remarks, that all the value is in IP. And, that unless there's innovation and IP that you're bringing to the table, you really cannot sit at that table. Now, we, on the other hand, I think over the last year or so have heard much less about the IP and the design and much more about the fab. And therefore, I think in his remarks, I would like to request Professor Paulraj to address that gap. Are we getting too focused on, building the fab capability? What are there lower hanging fruits within this ecosystem which we should leverage and take advantage of, is certainly a question. You also said that, uh, you know, uh, getting talent is a big challenge. And even in the US, getting funding for fabless is shrinking. If that is the case, then where is India going to get the talent and the funding for fabless, even if innovation in fabless is probably a lower hanging fruit? I'd also like to request him, in the light of the fact that we have almost quite a few months have passed since the US CHIPS Act and the EU Act, what is the kind of traction that is visible in the industry? What are the learnings, if any, for in India in this area? And as a late entrant, since he was, pointing to the fact that late entrants perhaps have to adopt a different strategy, we'd like to hear a little more about his thoughts on this. So I will stop at this point, but I'm sure we are looking forward to a robust discussion, given that there are very many knowledgeable discussants around the room. And with this, I will hand it back to the chair and to Professor Paulraj.
Thank you, Ms. Sundararajan. I think very useful focus on the challenges for India. Before I request Professor Paulraj to respond to the specific issues and questions that you have raised, perhaps I could invite our Secretary DST, Dr. Karandikar. Sir, would you like to make some remarks at this point? And,
Maybe I'll.
No problem. Then, if that's okay by the House, I'll make sure I get everyone on board to the extent we can. I'll request Paul sir to perhaps respond to what Aruna said on these 2 points.
Secretary Sundararajan for your comments. I think they covered a lot of very, very good points. On some specific questions, what should India do on the fab side of the industry? And as you know, we have tied up with Micron for the back-end fab. And I think it's a good start. What we have to do is that we'll initially get a lot of technology from Micron. And of course, we'll provide a lot of labor at the assembly line, but we should put in a lot of engineering inputs and try and advance the technology in the back end, because back end is getting more and more complicated also. There is something called chiplets, which is a slightly different version of the packaging of chips, as well as multiple layers of chips. So it's getting more complex. And there, if we can put a good team there and a good R&D there, so we make innovations in that. It's also going to be a joint venture between us and the Government of India, between Micron and Government of India. Make innovations there and try and make that facility in India more and more competitive with the world. So that is one thought. But the bigger prize is the fab, the front-end fab, the diffusion take. That's the high-tech part. I'm not entirely familiar with the current thinking in the government, but I think we will, I'm sure, land up with a credible fab partner. And once again, there too, because our base is so low, all the technology will be brought in by, and the skill manpower will come from our joint venture partner. But there's no reason why we can't also pump in people and do R&D and build our capability. And sometimes that learning from that joint venture, we can take people out and formally form an independent Indian company. I'm not quite sure how the equity is structured in these companies, but if it's 51% equity in India, then we have some control. If it's not, then we should use that talent grown there to form we will always need some partnerships, but we want partnership where it's Indian headquartered and at least 51% controlling interest. So, but the fabless, which he pointed out, that's I think is a much lower hanging fruit, because fabless is nothing more than ideas and tools. Tools are available. While unlike in fabs, where the entry ticket is many billions, the entry ticket in fabless is typically much lower. today, I think a reasonable fabless company to have any market success will probably have to raise about $50–60 million. Otherwise, it can't compete in the global ecosystem. But it's much, much smaller than a fab. So fabless is where I think we should focus on. We have something going for it, and we have a lot of operators, a lot of engineers in MNCs, but they tend to be in a different island. But where we have pulled out one or two, one of them was called Avnish Agarwal, one of my students from Stanford, who he pulled out and he's formed a wonderful company. It's still an American company, but operations a lot in India. And so similar examples of pulling out talent from there will be useful. And there is some ability within our country, but the key thing for them is the real venture capital. That is not available today. And the source of venture capital for us, originally in China and certainly in Israel, is always in the United States. And I think US venture capital is ready to come to India, but they're a business. They got to make money. Otherwise, they're not going to come here. So we need a number of mechanisms to attract them. And I can explain how China did and what Israel did. I know those two countries. So on the fabless side, I think venture capital is absolutely critical. And because we have already a scheme called DLI, but that's a very, very small scheme. And that also needs some changes, but which I won't discuss. But venture capital, and when US venture capital comes here, they'll bring a lot of industry knowledge, because they will bring board members, they'll bring, mentors. So they'll connect us to the Intels and the Qualcomms of the world. So because what I find in India today is we don't understand that ecosystem. So they will bring that, but they will only come if we give them some tailwind and the different models, how that is done. So to answer your question there, I think fabless is really low-hanging fruit. We didn't need to do everything, but fabless is where we can make the fastest progress. And also there, I mentioned earlier, there are lots of Indian origin, NRIs, or maybe US citizens, it doesn't matter, who have done 2-3 companies, have learned a lot of industry knowledge. We should try and attract some of them back to set up companies here. Because when they come here, they come with a lot of knowledge, connections, and usually if they come, VCs will write checks for them because they know they have a chance of succeeding. In the United States, most times the first 2 companies fail. Only the 3rd company, you learned enough to try and make it a success. So somebody has experience to be very, very useful to us. So on the fabless side, I think many things should be done, and we have to worry about IPR issues, M&A issues. It needs at least 20, 30, 40 people who understand the industry to guide the government. Right now, that knowledge is not there in our country. It's absolutely critical we form that group. Otherwise, we'll be heading in directions which will not work out, in my opinion. So, therefore, I think I'm still absolutely confident that we can do it, but we should not underestimate the challenges. But most of all, in my last slide, I kept saying, we've got to understand the barriers of the industry. And that understanding is missing in our country. So that is the key to our success. So we have to bring that understanding in, and I'm sure we can find people who can work with us 1% time to 100% time to make that happen. Secretary Sundararajan knows I come more than a dozen times to India trying to push these ideas, but I'm getting old now. I like to bring some junior partners to help out. So, thank you.
Thank you, Paul, sir. I think that was a very useful response to what Secretary Sundararajan had raised. I have a couple of questions actually for both of them, but I'll wait till I can recognize Professor Panchakeshan, sir. I'm looking at you. The IIC's lead scientist come academic.
I am 90 years old, so I'm not really au courant with what is going on in the country, but I would like to briefly take a few minutes to say about the first semiconductor industry in India. It was started by my classmate, who was Gurpreet Singh. He was in Doon School, and his father had a cold storage, so he had a lot of money. He did not do science, but after passing out from St. Stephen's College, he started an industry for making transistors. It was called Continental Devices. And to run it, he got my brother-in-law, who was in Philips in Holland. My brother-in-law came back with his Dutch wife to India and set up the factory. And he had very young people with him, and he was very enthusiastic about it. And one very good thing he did was he persuaded one of the persons who to go to America. That was Vinod Dham. He went to America and discovered the Pentium, discovered or invented or whatever you call it. And he made a lot of money, and that helped the other people who were also in transistor to go there. But after that, Gurpreet's children were not interested in continuing the factory. The factory is still in existence. It makes transistors, but supplies spare parts to the army for their old things which still use transistors. So I'm just telling this story to say what kind of difficulties are there and what are going. And one other thing that I would like to mention is that Bardeen was one of the persons who discovered the transistor. He also later discovered what is behind superconductivity. Many more people in India worked in superconductivity than in transistors because here theoretical physics is more concentrated than the other one. But now that you see, I think I will leave the field floor for the present discussions.
I should mention that Vinod Dham and I are both some kind of advisors to the government on the fabless side.
I'd be happy to, yes sir, you kindly introduce yourself because we are recording this and then we'll request.
Sir, my name is Rakesh Mehrotra. I work with the Samsung R&D. I just wanted to find, but I'm an Indian, not a Korean. So I just wanted to find it out. What's your observation if the Taiwan falls? What India can get out of it? Are we ready for that?
Out of Taiwan?
Exactly, sir.
That if Taiwan is taken over by China, what is it that India can possibly?
That is us.
Sir, my name is Sanjay. I'm a journalist. My question is that, in the 90s, we see these big software companies, the TCS, Wipros, and, all these big companies, $1 billion. Why don't we have the same success with the semiconductor? What was that we didn't have in India, that we could, enable our IT and ITS business to billions and billions of dollars and not to the semiconductor side? What, in your observation, could have been the reason?
How will the Arogyaswami, how do you expect the 1,000 sources for materials for semiconductors to constrain the American effort at revival within the states, within the USA?
Sir, my question is regarding Sir Uday, quantum computing and how it's going to help Indian economy. And second is about